Hello everyone. So this is the first hour out of the 6 hour where we are going to talk about optics. In these 6 hours, I will try to make you accustomed with understanding that how do rays move through the medium. And you will be able to visualize where the image is getting formed, the image is magnified or the image is diminished. You might think that why sir is taking 6 hours on this single topic. The reason is that optics is scoring. Optics requires concepts which are a little bit difficult to understand. At the very same time, optics is the topic where you can answer any question without raising pen if you are good at understanding. Personally, I don't use the mirror equation 1 by v plus 1 by u equals to 1 by f. Why? Because I use the Newton's formula, which makes it very easy to solve the question based on optics without even raising pen. So in this 6 hour series, we are going to practice all those things. But we need to start from the basic. So let's start today's hour where I'm going to talk about plane mirrors. So let's start this hour. And in the first hour, the first thing I'm going to talk about is reflection. So let's talk about reflection of light. So what is the definition of reflection? You have to be very patient in understanding the definition. You have to be very patient in understanding the sign convention. And once you know it, this is a very easy game to play. So let's start. When a ray of light, after falling on a boundary separating two media, comes back into the same media, then this phenomenon is called reflection of light. So let's say you have a boundary separating out two media, air and glass. You can see here a ray of light is incident and this ray of light gets reflected. So it is again into the same medium. It is again traveling into air now. This phenomenon is called reflection. Now let's say the angle made by the incident ray and the reflected ray with the normal is given by I and R. So the law of reflection tells us that the angle of incidence is equal to the angle of reflection. But this is not the complete law. The complete law goes like this. The angle of incidence is equal to the angle of reflection and the incident ray, reflected ray and normal lies in the same plane. So you can't have this type of phenomena that you have a surface where the light ray is incident and here you have got the normal and after reflection the ray is coming out of the plane. That can't happen. The incident ray, the normal and the reflected ray all lie in the same plane. So what is law of reflection? First thing, the angle of incidence is same as the angle of reflection. Yes sir. Second thing, the incident ray, the normal and the reflected ray, all three of them lie in the same plane. Now I asked you a question. Law of reflection works for a flat surface or does it even work on a curved surface? The answer is that law of reflection even works on a curved surface. Let's say you have a curved surface. And on this curved surface, which is reflecting in nature, a ray of light is incident. How will this light ray go after the reflection? To understand this, you need to draw the normal at the point of incidence. So visualize a normal here. Let's say the incident ray makes an angle theta with this normal. Then after reflection also, this ray will make the same angle theta with the normal because that's what the law say. The angle of incidence equals to angle of reflection. There is one more thing that we can say using the second argument that the incident ray, the normal and the reflected ray lie in the same plane. The thing we can say is that if we visualize three vectors, one along the incident ray, one along the normal and one along the reflected ray. Now as all these three vectors will lie in the same plane, if I take cross product of any two of them, it will point in the direction perpendicular to the plane. If the incident ray, reflected ray and normal lie in the same plane, if I take cross product of any two, it will lie perpendicular to the plane because we get the direction in case of cross product from the right hand thumb rule, right? So listen to this statement carefully. It's an important statement. The statement goes like, so if we assume vectors along incident ray, reflected ray and normal, the dot product of any one with the cross product of other two is 0. Let's visualize three unit vectors along the incident ray, reflected ray and normal. And let's call these three unit vectors as I cap, a unit vector along the incident ray, R cap, a unit vector along the reflected ray and N cap, a unit vector along the normal. As we know that these three vectors lie in the same plane. If I take cross product of any two of them, let's say I take r cap cross n cap, it will be perpendicular to the plane. Or if I take I cap cross n cap, that will also be perpendicular to the plane. Or if I take I cap cross r cap, that will also be perpendicular to the plane. Now, the cross product of any two will be perpendicular to the plane containing these three vectors. And we know that the dot product of two perpendicular vector is 0. So if I take dot product of r cap cross n cap with, let's say, I cap, then since I cap lies in the plane and r cap cross n cap lies perpendicular to the plane, their dot product has to be 0. Similarly, if I take r cap dot I cap cross n cap, I cap cross n cap is a vector. You are doing cross product. It will be perpendicular to the plane. And r cap is in the plane. And we know that the dot product of two perpendicular vectors is 0. So their dot product will also be 0. Or if I take n cap dot I cap cross r cap, that will also be equals to 0. So this statement is a simple statement, theoretical statement, important statement. Statement goes like, so if we assume vector along incident ray, which I called I cap, reflected ray, which I called r cap, and normal, which I called n cap, the dot product of any one with the cross product of other two is 0. So this is the statement you should know. Now before we talk ahead, we need to understand some important points about the law of reflection. This first statement I am telling will be used in the chapter of wave optics. This is important. And we have talked about this while learning waves as well. The statement goes like, there is a phase change of pi. There is a phase change of pi if reflection takes place from a denser medium. I know that all of you know that out of air, water, and glass, glass is the most optically dense, then comes water, then comes air. Glass has got refractive index of 3/2, which is 1.5. Water has got refractive index of 4/3, which is 1.33. And we take the refractive index of air to be nearly 1. Now let's say you have got this case where you have got on the top water and under it you have a glass slab. If a ray of light is moving in glass, which is optically denser medium, and this ray gets reflected, then this ray is getting reflected from a rarer medium. Water is the one reflecting it. So it undergoes no phase change. So the phase change is 0. But when a ray of light gets reflected from a denser medium, it undergoes a phase change of pi. So if the ray of light is traveling in water and it gets reflected by a denser medium, which is glass in this case, then it undergoes a phase change of pi. So here you will say that the phase of this wave will change by a phase angle of pi. So remember this thing. We will revise this again in wave optics, but it's better to know this from here onwards only. There is a phase change of pi if reflection takes place from denser medium. The next point, again we have done this in waves and it's important, you should know this. The next statement goes like, after reflection, the velocity, wavelength and frequency of the light remains same but the intensity decreases. We know that the reflected ray is in the same medium as the incident wave. If the reflected ray and incident ray are in the same medium, they need to have the same speed. Yes, sir. Since the frequency depends upon source and not at all on the medium, whatever is the frequency of the incident ray, the same will be the frequency of the reflected ray. And from V equals to F lambda, since the reflected ray has the same velocity as the incident, as they are in same medium, and the reflected ray has the same frequency as the incident, they are bound to have the same wavelength. So sir, what changes? What changes is the intensity, what changes is the amplitude. The amplitude of the reflected ray is less than the amplitude of incident, given that some part of the electromagnetic radiation has been absorbed or has been transmitted. If you think of a particular case where 100% reflection is taking place, like in the case of total internal reflection, then the intensity of reflected wave will be same as that of incident. Otherwise, in real world, whenever light ray is incident, some part gets absorbed or some part gets transmitted. If some part of the energy gets absorbed or transmitted, the reflected energy has to be less. If the reflected energy has to be less, the reflected amplitude will be less, the reflected intensity will be less. The reflected intensity will be same as incident intensity in the case of total internal reflection, because there 100% reflection takes place. The next point, if a light ray is incident normal to the surface, after reflection it retraces its path. Again, this might look like a simple point, but this is important point. So if you have a mirror and you incident a ray on it normally, such that the angle of incidence is 0, then you will say that the angle of reflection also have to be 0. So the light ray will retrace its own path. Now in such a case, you will say that the light ray has retraced its path, so the light will be going back to the same place from where it came out. Now this particular concept is important wherever you find a question where the image is formed on the object itself. If the image is formed on the object itself, it means that light has somewhere retraced its path. And for the light to retrace its path, it must have hit a mirror normally. Once more, in many a question you will find this concept that the final image is formed on the object. If the image is formed on the object, it means that the light has retraced its path. And for the light to retrace its path, the light should hit a mirror normally. So every time you find this question that the final image is formed on the object itself, just make sure that the ray must be hitting a mirror normally. It means that the angle of incidence when it hits a mirror is 0. So now let's see an example. So there is this question. The question goes like, if the incident ray is along a vector 2i cap minus 3j cap, determine the direction of the reflected ray. So along which vector you will say that the reflected ray is going. Now you have learned in the chapter of collision that if there is a perfectly elastic collision, then in a gravity free space, if a ball hits with a speed v, it will bounce back with the same speed and the angle of incidence will be same as the angle of reflection. Who did the study on collision? Sir Isaac Newton. Who said that light is made up of teeny tiny particles called corpuscles which collide elastically? Sir Isaac Newton. So Newton assumed that light is made up of some small particles which collide elastically. So these type of questions are very easy questions. You just need to remember that the vector along the normal flips. When I say 2i cap minus 3j cap, it means that component this way is 2, along the x is 2, and the component towards y is minus 3 downwards. After the incidence of the ray, the vector along the normal flips. Since the mirror is in xz plane, the normal will be in y direction. So just flip the y component. So the reflected ray will move this way. These two angles will be equal. The reflected ray will get its component along the normal flipped. So this component will remain the same 2 and this component will flip and you will get upward 3. So you will say that the reflected ray has to be along a vector 2i cap plus 3j cap. That's how easy it is. So the vector along the normal flips. So you will say that if the incident ray is along the vector 2i cap minus 3j cap, the reflected ray will be along the vector 2i cap plus 3j cap. Now this example has been taken to make you understand that the vector along the normal flips. Let's complexify this question a little bit more. Let's see this example. On a mirror parallel to yz plane, you need to visualize the yz plane. So x, y, z. So the mirror is parallel to yz plane, this plane. And the question goes like, on a mirror parallel to yz plane, a ray is incident along the vector 2i cap minus 3j cap plus 4k cap. Find the vector along the reflected ray. Now you might think that I need to visualize along the x velocity is 2, along the y velocity is 3 downward, along the z velocity is 4 outward, and the vector of incident ray is going something like this. You do not need to do all this. You just need to understand that the component along the normal flips. If you have got x, y and z axis and the mirror is parallel to YZ plane. For this YZ plane, can you tell me the direction of normal? That the normal will be along the x-axis. So the component of the incident ray along the normal will flip. Which component is along the normal? So normal is along x-axis. So this 2I cap is along the x-axis. This one will flip. So in place of 2I cap, just write minus 2I cap, game over. So you will say that for a mirror in YZ plane, the normal is along the x-axis. So the vector along the x-axis will flip. And the vector along the x-axis is 2I cap. Hence, a vector along the reflected ray will be given by minus 2I cap. In place of 2I cap, just write minus 2I cap, minus 3J cap and 4K cap. The components along the plane remains the same. The component along the normal flips. This is a simple question which you should know how to answer. Let's see the theory ahead. Now, this is a constant doubt with the students. This image is real or virtual? This object is real or virtual? So as to never get confused between real and virtual, you need to know their definition. So let's start first by talking about what is object and what is image. Let's talk about object. The point of intersection of incident rays or their extension is called the object. The point of intersection of incident rays or their extension is called the object. First of all, let's talk about reflection only. So let's say you have a plane mirror. On the plane mirror, you can have convergent beam being hit on it, or you might have a divergent beam being hit on the mirror. If the incident rays do not actually intersect, but their extensions intersect, you say that the object is virtual. If the incident rays actually intersect at a point, you say that the object is real. So the point of intersection of incident rays or their extension is called object. Next definition, the point of intersection of reflected, which we will first talk about, or refracted rays or their extension is called the image. So the place where incident rays intersect is called object. The place where reflected or refracted rays intersect is called image. Do not worry, these things will get clearer when I will take some examples. Stay tuned. Now, what is the meaning of real? If the rays actually intersects, it's real. If the incident rays actually intersect, you call it real object. If the reflected or refracted rays actually intersect, you call it real image. What is the meaning of virtual? If the extension of the rays intersect, then it is called virtual. If the extension of incident rays intersect, you call it virtual object. If the extension of reflected or refracted rays intersect, you call it virtual image. Sir, I am not getting all these definitions. I will ask you, if you haven't understood, just pause the video once, revise these four, and then play the video, because now I am going to take the examples that will make you understand them. But it's important that you get the definitions first. Now let's see some example. Let's say you have got this plane mirror, and let's say a convergent beam is being hit on the mirror. Can you tell me, do these incident rays intersect? No, they do not actually intersect, but their extension does. Since their extension intersect, the point of intersection of incident rays is called object. But are these rays actually intersecting? No, sir. Their extension is intersecting. So you will say that since the extension of the rays are intersecting, this is a virtual object. Now we have learned the law of reflection. Since we have hit a convergent ray on the plane mirror, after reflection, the rays will bounce back. Now following the law of reflection, as the rays bounce back, you can see that these two rays are the reflected rays. My question is, are these reflected rays actually intersecting? Yes, sir, they are actually intersecting at this point. We have learned that the point of intersection of reflected or refracted rays is called image. And if the rays actually intersect, then it's real. So you will call this point to be real image. Do notice here one important concept. This is asked, can a plane mirror form a real image? Yes, a plane mirror can form a real image given that the object is virtual. So when does the plane mirror form a real image? When the object is virtual. For a virtual object, a plane mirror forms a real image. This is an important concept covered here only. Let's see next example. On the same plane mirror, if we place an object in front of it, from this object rays will come out. Now these rays which are going to incident on the plane mirror, they are called incident rays. Are these rays actually intersecting at a point? Yes. What is that point? Object. This is a real object or a virtual object? So this is a real object because these incident rays are actually intersecting at this point. So you will say that this is a real object. Now after reflection, these rays will bounce back. So these two rays represent your reflected rays. My question is, are these reflected rays actually intersecting? No, sir. But if I extend them, then so their extension will intersect. So when the extension intersect, you call it real or virtual? Sir, when extension intersect, we call it virtual. And the point of intersection of reflected or refracted rays is called image. So in this case, your image will be a virtual image. To understand it more deeply, let's see two more examples. Let's take this case. You have got a concave mirror. And let's say on this concave mirror, you have got these parallel beam of light hitting. Now here at the point of incidence, think of the normal. From the law of reflection, the angle of incidence has to be same as the angle of reflection. So these two angles have to be equal. So these parallel beam after getting reflected from this concave mirror will go like this. My question is, are these reflected rays actually intersecting or are their extension intersecting? So they are actually intersecting. So that's why this point will be a real image. If you have got, let's say this example where you have a convex mirror and you have got these parallel rays hitting it. Using the law of reflection, you can say that law of reflection even works on a cut surface. To use it, I need to draw normal here. So draw the normal here and draw the normal here. The angle made by incident ray with the normal will be equal to the angle made by reflected ray with the normal. These two angles will be equal. And the angle made by incident ray with the normal has to be equal to the angle made by the reflected ray with the normal. These two angles has to be equal. So you will say that after reflection, the two rays will go something like this. Now my question is, are the reflected rays whose point of intersection gives you image actually intersecting or are their extensions intersecting? So their extension will intersect. So you will call this a real image or a virtual image. So when the extension intersect, it's a virtual image. So here in this case, you will say I'm getting a virtual image. Now let's take an example from refraction. Here you can see that we have a converging lens. Now let's say on this converging lens, we have got a convergent beam hitting. The point of intersection of incident ray is called object. My question is, are these two rays actually intersecting? No, but their extension will. So which type of object you will call it? You will say that, sir, a virtual object is placed here because the incident rays are not actually intersecting, their extension is. So you will say that we have got a virtual object. Now what does a converging lens do? Sir, a converging lens converges. So it will further converge these rays hitting it. So once it converges, the refracted rays go something like this. Now we know that the point of intersection of refracted rays is called image. You will call this image as real image or virtual image. So here the refracted rays are actually intersecting. So this is a real image. Now I am going to tell you one important statement based on this particular concept. If you have a converging lens and if you have a virtual object, a converging lens will always form a real image of a virtual object. A converging lens will always form a real image of a virtual object. So why are you saying so? If you have got beta a virtual object, it means that the incident rays are converging in nature. Yes, sir. And what does the converging lens do? Sir, it converges them further. So once this converging lens converges the rays further, they are definitely going to meet. And once the refracted rays will meet, you have got a real image. So for a virtual object, you are always going to get a real image. Now this is a concept you should know. Let's take one more example for the case of diverging lens. If you have a diverging lens and you have placed an object in front of it. So since the incident rays are actually intersecting at a point, you will say that we have got real object. What will the diverging lens do? Sir, the diverging lens will diverge the rays, right? Now once the diverging lens will diverge the rays, will these two refracted rays ever meet? No. What will meet? Sir, their extensions. So once you extend these two refracted rays, you will find their point of intersection. Now tell me, this is which type of image? Sir, this is a virtual image. Now listen to the argument carefully. It's an important statement because when these type of statements come in the examination, students try to answer them using equation. You do not have to use the equation here. You need to focus on the concept. Can I say that for a real object, a diverging lens will always form a virtual image? For a real object, a diverging lens will always form a virtual image. Yes. Why? Because out of the real object, the rays which are coming out and which are going to hit this diverging lens are going to be divergent rays. And this diverging lens will further diverge the rays. So the refracted rays won't intersect. What will intersect? Their extension. So you will always get a virtual image for a real object when you place it in front of a diverging lens. And you will always get a real image of a virtual object when you place this virtual object in front of a converging lens. So see, here you have learned two important concepts which if you use equation to solve will be difficult to explain. So now we will talk about the image formed by a plane mirror. So the image of a real object. So if you actually place some object in front of mirror, formed by the plane mirror is virtual, erect, laterally inverted, equal in size of the object and at a distance equal to the distance of the object in front of the mirror. Now here you can understand each term. If you place a real object in front of the mirror, the incident rays will be something like this and the reflected ray something like this. Do the reflected ray intersect? No, their extension does. So you will say that the image formed is virtual. Remember that for a real object, a plane mirror forms virtual image. For a virtual object, a plane mirror forms real image. The image will be erect. So if you have a plane mirror and you place a pen in front of it like this, the image will also point in the same sense. When I look in the mirror, my head is up and my feet are down, just the way I am standing. So it's erect. But sir, then it says laterally inverted. If you point a finger towards the mirror, or let's say if you have a pen pointing towards the mirror, when you look at the image in the mirror, the point will be towards you. So it's laterally inverted. So if you have placed object this way, the image will look this way. It's laterally inverted. So the things which are closer to the mirror, their images are also formed closer to the mirror. And the things which are farther away from the mirror, their images are also formed farther away from the mirror. So the image appears laterally inverted. Next thing, the size of the image is same as the size of the object given that the image is being formed by plane mirror. And the distance of the image is equal to the distance of the object in front of me. So visualize that you have got this object placed in front of plane mirror. The image looks like this. And the distance of the object from the mirror is same as the distance of the image from the mirror. Nothing shusha here, everything basic. Talking about deviation produced by a plane mirror. Let's say you have got this plane mirror and a ray of light is incident on it. We know that once reflected, this ray will go somewhere this way. Now question is, what is the deviation produced in this ray due to reflection? So you will say that, sir, if you visualize the normal, we know that the angle of incidence will be same as the angle of reflection. This ray was going straight and was destined to go straight, but it got reflected due to the presence of plane mirror. And due to the presence of the plane mirror, it is now going along the path of the reflected ray. So how much deviation is produced? So you will say that, sir, this angle is the deviation. Now how to find it? It's very easy. You will say that this whole angle is 180 degree. And since we know that the angle of incidence is same as the angle of reflection, in place of angle of reflection also I can write I. So can I say that I plus delta, 2I plus delta equals to 180 degree. So the deviation produced is nothing but 180 minus 2I. In place of angle of incidence, you can even write the angle of reflection R. So just remember that the deviation produced by a plane mirror on a ray hitting it is nothing but 180 minus 2 times the angle of incidence. So easy. But here comes one important case. The case goes like deviation produced by two inclined plane mirrors. Let's say you have got two plane mirrors inclined to each other at some angle theta, and a ray of light is incident on one of them, and after undergoing two reflections on both the mirrors, the ray comes out. Question is, in this case, what is the angle of deviation? So you will say that the incident ray is this, yes, and the final ray coming out is this. So this ray has turned its path by how much angle? So this ray was going this way, yeah, and now it's going this way, yes. So what is the deviation? So it has turned twice, once and then once more. So you will say that the total deviation is given by this angle, and let's call this angle delta. Sir, how to find this angle delta? I will tell you how to find delta. First of all, tell me if this angle comes out to be alpha, what will be the relationship between alpha and delta? So you will say, sir, here this angle is 180 degree. The whole angle is delta. So I can say that delta equals to 180 degree plus alpha. So let's find out alpha so that I can tell you what is the value of delta. Now, bacho, here I will use one simple concept. If the incident ray makes an angle I with the normal, then the angle made by the incident ray with the plane of the mirror will be nothing but 90 minus I, right? Let's say for this first reflection, the angle of incidence is I. So if the ray is hitting the first plane mirror with an angle of incidence I, it will also be reflected at the same angle I. And this angle made by the reflected ray with the plane of the mirror will be 90 minus I. Now let's say this ray, when it hits the second mirror, hits at an angle of I dash. So the angle made by the incident ray with the plane of the mirror will be nothing but 90 minus I dash, and this angle will also be I dash from the law of reflection. Now here you can look in two triangles. One, this triangle having the angle theta 90 minus I dash and 90 minus I, and the second triangle having angle 2I, I plus I, 2I, 2I dash and alpha. And you can write two equations from here. The first equation, looking in this triangle having angle theta 90 minus I and 90 minus I dash, you will say that theta plus 90 minus I plus 90 minus I dash, the sum of internal angles has to be equals to 180 degree, and 90 plus 90 becomes 180. So this 180 and 90 gets cancelled, so you get theta equals to I plus I dash. The second equation you can write by looking into this triangle having internal angle as 2I, 2I dash and alpha. You can write 2I plus 2I dash plus alpha equals to 180 degree. Or you can say that alpha equals to 180 minus 2 times of I plus I dash. In place of I plus I dash, you can substitute theta. So you get alpha equals to 180 minus 2 theta. And if alpha equals to 180 minus 2 theta, then delta, which is 180 plus alpha, will be given by 180 plus 180 minus 2 theta. So your total deviation comes out to be 360 degree minus 2 theta. So you need to remember this result. The deviation produced by two plane mirrors inclined at angle theta when a ray of light undergoes reflection from both the mirror ones is given by 360 minus 2 theta. And notice that this result is independent of the angle of incidence. What is the angle of incidence? It doesn't matter. The deviation produced will be 360 minus 2 theta. So now comes one very important case. If you have got two plane mirrors inclined to each other at angle of 90 degree, then can you tell me what will be the deviation produced? Yes sir, 360 minus 2 times of 90. 360 minus 2 times of 90 will be 360 minus 180, that will be 180 degree. So no matter at what angle a ray of light is incident, the reflected ray finally coming out will be anti-parallel, deflected by an angle of 180 degree with respect to the incident ray. So this result is something that students do not remember usually, and this is important result, simple result. So if you have got two plane mirrors inclined at angle theta and a ray of light is incident, and after going reflection on both of them once, if the ray of light comes out, then the deflection produced in the ray is given by 360 minus 2 theta, and the result is independent of the angle of incidence. This is important. Now let's talk more. Now let's talk about the rotation of mirror. So if a plane mirror is rotated in the plane of incidence through an angle theta by keeping the incident rays fixed. Now this is the problem. Students remember a result but they do not remember when to use it. So here, when the mirror is rotated by an angle theta, keeping the incident ray fixed, the reflected ray turns through an angle 2 theta. So what is the logic? Simple logic. Think that you have a plane mirror on which the incident ray is hit normally. So the angle of incidence comes out to be 0. The angle of reflection will also be 0. So the ray will retrace its path. If now you turn this mirror by some angle theta, keeping the incident ray fixed, if you turn the mirror by some angle theta, then its normal, which is perpendicular to the plane of mirror, will also turn by the same angle theta. So now the normal will be somewhere here. Keeping the incident ray fixed, if the mirror is turned by angle theta, the normal will also turn by angle theta. So the normal, which was in direction of the original incident ray, will now make an angle theta with it. And the reflected ray should also make an angle theta with the normal from the law of reflection. So if you turn the mirror by an angle theta, then the reflected ray turns by an angle 2 theta. This is the basic argument. So keep this in mind. If you turn the mirror by an angle theta, then the reflected ray, which was going normally initially, would have now turned by an angle 2 theta. Easy. So now we will talk about, if you have got two plane mirrors inclined at some angle theta, what are the number of images formed by them? But before I go there, let's see an example that will make our concepts clear on the number of images. So let's take a simple case. When you have got two plane mirrors M1 and M2 inclined to each other at an angle of 90 degree. And let's say their point of intersection is taken as the origin 0, 0. And there is an object placed in front of them and the object has coordinates 2, 3. The question asked from us is this. Locate all the images formed of the object with coordinates. So at which coordinates you will get the image of this particular object. So you will say, sir, it's easy. First of all, I will look at the object and the mirror one. And let's say the mirror one forms an image and it will form it somewhere here. Let's say this image name is I1. When the mirror one forms the image, it does not change the y coordinate. It only flips the x coordinate. So for this particular image, the x coordinate will be -2 and the y coordinate will be same 3. When the mirror 2 forms the image of this object, let's say it forms somewhere here. Let's call this particular image as I2. When the mirror 2 forms the image, it won't change the x coordinate, it will just flip the y coordinate. So now when the mirror 2 flips the y coordinate, you will get coordinate of 2, -3. you will say that this mirror 2 will form the image of the image formed by the mirror 1. This mirror 2 will also form one image of I1, and the image of I1 when formed by mirror 2, it will simply flip the y coordinate, it won't flip the x coordinate. So it will form one image here without changing the x coordinate, which is -2, at -2 comma -3. And similarly, the mirror 1 will form an image of I2, and when mirror 1 will form the image, it won't change the y coordinate, it will simply flip the x coordinate. So when the x coordinate flips from 2 comma -3, you will again get -2 comma -3. So you will say that M1 forms one image of I2, M2 forms one image of I1, and these two images coincide at the coordinate -2 comma -3. Let's call this image I3. So the first question, how many images are formed? Sir, 1, 2 and 3. Now, if you visualize the coordinates of object as well as these three images, you will say that the coordinate of object is 2 comma 3. The coordinate of I1, the first image formed by M1, is -2 comma 3. The coordinate of I2 is 2 comma -3, and the coordinate of I3 is -2 comma -3. If I ask you what is the distance of object from the origin, you will say that under root of 2 square plus 3 square. If I ask you what is the distance of I1 from the origin, you will say under root of -2 square plus 3 square, but -2 square becomes as good as 2 square. So these two distances will be same, let's call them R. Similarly, if I ask you what is the distance of I3, you will say under root of -2 square plus -3 square, but once you square, -2 square is as good as 2 square. So this distance will also be R, and by the same logic, this distance will also be R. So the object plus all the images lie on a circle with the center at the origin, right? So these are the things you need to remember. So bachcho, first, image formed by M1 for the object will be at -2 comma 3. Yes sir. M1 will flip only the x coordinate, not the y coordinate. Image formed by M2 will be at 2 comma -3. M2 will flip only the y coordinate, it won't change the x coordinate. Then the image of the image formed by M1 forms some image here which we call I1. The image of the image formed by M1 by M2 will be at -2 comma -3, somewhere here. And this will also be the image of the image formed by M2 further formed by M1. So the image formed by M2 further formed by M1. So M1 will also form the image of I2 at I3. And the last important point which we have learned is that all the images plus object will lie on the circle with the center at the origin, because their distances comes out to be same. Now I am going to tell you ready-made formula. If they give you any random angle theta between the two plane mirrors, then how to identify the number of images. So let's start. The number of images for two inclined mirrors. Let's say you have got two inclined mirrors at an angle theta, and there is some object placed between them. Then how to identify the number of images? So when two plane mirrors are inclined to each other at an angle theta, the first thing that you have to do is find the value of 360 by theta. So you will say that find M, where M is nothing but 360 by theta. So if they say that there are two mirrors inclined at angle of 30 degree, then your M will be nothing but 360 by 30, and that will give you 12. If you have got two plane mirrors inclined with each other at angle of 45 degree, then your M will be 360 by 45, and 360 by 45 will give you 8. Your first job is to find M, where M is nothing but 360 by theta, where theta is the angle between the two plane mirrors. Now, there can be multiple cases. What will this value M come out to be? So for each case, you have to remember the result. So if M comes out to be even, if M comes out to be 2, 4, 6, 8, even number, then the number of images is m minus 1. So for the example I just took, if you have got two plane mirrors inclined with each other at an angle of 30 degree, then you will say that the value of m, which is 360 by theta, will be 360 by 30, which is 12. And we know that this 12 is an even integer. So if you get m as even integer, 12 is an even integer, then the number of images is m minus 1, that will be 12 minus 1, you will get 11 images. Irrespective of where is the object placed between the two mirrors, the number of images will be 11. The next case, if m is odd integer, then the number of images can be found under two possibilities. If m is odd, then there are two cases. Case 1, if the object is placed symmetrically, or case 2, when the object is placed asymmetrically. So what is the meaning of object placed symmetrically? Let's say there are two plane mirrors inclined at angle theta, and the object is placed such that the line joining the point of intersection with the object makes equal angle with both the plane mirrors, theta by 2, theta by 2. So if the object is placed symmetrically, you get one answer. If the object is placed asymmetrically, such that this line makes different angle with both the plane mirrors, you get different results. So if you get m as even integer, then irrespective of the position of the object between the plane mirrors, the number of images is m minus 1. If you get m as odd integer, then there are two cases. Case 1, when the object is placed symmetrically. Case 2, when the object is placed asymmetrically. When the object is placed symmetrically, you get lesser number of images, same as in the first case, you get m minus 1 images. So number of images comes out to be m minus 1. When you place the object asymmetrically, then you get more number of images. And the number of images in this case comes out to be m. So first of all, find out m. M is 360 by theta. If m is even, then the number of images is m minus 1. If m is odd, let's say 5, 7, 9, 11, then you have to reconsider the case. If the object is placed symmetrically, such that the line joining the point of intersection of plane mirror and the object makes same angle with both the mirrors, then the number of images are m minus 1. And if this line makes different angle, then the number of images is m. But sir, all numbers can't be even and odd. Sir, tell me 3.67 is even or odd? No, it's neither even nor odd. It's a fraction. So better then, if you get a fraction, then what to do? So if m is fraction, then the number of images is equal to the greatest integer smaller than the number. What? If you get 360 by theta on solving, let's say equals to 6.87. If you choose such a value of theta, such that 360 by theta comes out to be 6.87. You can't get 6.87 images, right? The number of images either have to be 1, 2, 3, 4. They have to be proper integer. So you have to look at the greatest integer smaller than this. The greatest integer smaller than 6.87 is 6. So if you get 5.334, the number of images will be 5. If you get 4.982, the number of images will be 4. You just have to think of the greatest integer smaller than this number. The students have this bad habit that they say if I get 4.982, I will round it off and the answer should be 5. No. You have to think of the greatest integer smaller than the number. So even if you get 9.999999999, then 2, you should report the number of images as 9. Do not round it off to 10. Okay. So beta, there are three cases. Case 1, the number even integer, the number of images is m minus 1. If you get odd integer, then you have to re-verify if the object is placed symmetrically or if the object is placed asymmetrically. If the object is placed symmetrically, you get lesser number of images and the total number of images is m minus 1. If the object is placed asymmetrically, then the number of images is m. And if m comes out to be a fraction, then think of the greatest integer smaller than that number. Let's practice some question based on this so that these formulas will set in our brain. So the first example, let's say beta theta is 36 degree. Now how many images will be formed? Your first job is to find 360 by theta. So you will say 360 by 36, that is 10. It's an even integer. If you get even integer, then the number of images is m minus 1. Since your m came out to be 10, you will say that the number of images is 10 minus 1, which is 9. If they give you theta is 72 degree, then you will do 360 by 72 to first find out the value of m. 360 by 72 gives you 5. 5 is odd. If you have got odd number, then there are two cases. If the object is placed symmetrically, then the number of images are m minus 1. You will get 4. If the object is placed asymmetrically, then the number of images is m. You will get 5. So if placed symmetrically, the number of images will be m minus 1, 4. If placed asymmetrically, then the number of images will be 5. Let's think of next example. If theta is 45 degree, then how many images will be formed? So find out 360 by theta, 360 by 45, that comes out to be 8. You get an even integer. So the number of image has to be m minus 1, you will get 7. So you will say that the number of images will be 7. If you get theta equals to 80 degree, now how many number of images will be formed? So sir, simply do first of all find out m. That will be 360 by theta. For this case, theta is 80. Doing 360 by 80, cancel out 0, 0. You get 36 by 8. 36 by 8 is 18 by 4. 18 by 4 is 9 by 2. 9 by 2 is 4.5. I'm getting a fraction. You can't have 4.5 image. You can have 4 image. You can have 5 image. You can have 6 image. You can't have 4.5. Right? So I have to think of the greatest integer smaller than 4.5. And the greatest integer smaller than 4.5 is 4. So I will say that the number of images will be 4. Let's see the next example. If theta equals to 50 degree, now tell me how many images will be formed. So again, first of all, find out m, which is 360 by theta. 360 by 50 gives you 36 by 5. And 36 by 5 will give you 7.2. 7 5s are 35. There is one extra. 1 by 5 is 0.2. So you get 7.2. Now again, you got a fraction. If m comes out to be 7.2, how many images will be formed? So think of the greatest integer smaller than 7.2, that is 7. So you will say that the number of images will be 7. Now we will see the case of velocity of image for moving object and mirror. I know that you have seen these type of questions where there is a mirror, where there is a person. The person has some velocity along the normal. Let's call it x. The mirror has some velocity along the normal. Let's call it y. The person also have a velocity parallel to the plane of the mirror. Let's call it z. And the mirror also have a velocity in its own plane. Let's call it w. And now they might ask you, what is the velocity of the image? It's easy to find, but I'm going to break down this process step by step. I am going to explain here what happens to the velocity of image due to the velocity of object along the normal. What happens to the velocity of image due to the velocity of mirror along the normal. What happens to the velocity of image due to the velocity of the object parallel to the plane of the mirror, and what happens to the velocity of image due to the velocity of the mirror in its own plane. So let's break it down step by step, understand the implication of all four, and then solving a question will be really easy. So let's think of the first case, when the mirror is fixed and the object is moving. So when the object moves with a speed u towards or away from a plane mirror, then the image also moves towards or away with the speed u. So let's say there is a mirror and you are walking towards the mirror, let's say with a speed of 2 meters per second. So you know that when you move towards the mirror, your image also move towards you. The image also move towards the mirror. So if you have a velocity of 2 meters per second towards the mirror, your image will also have a velocity of 2 meters per second towards the mirror. But do understand that the direction of these two velocities are different. If you start moving away from the mirror, the image will also start moving away from the mirror. So think of the first case. When you have a velocity, let's say v, towards the mirror, the image will also have the same speed but in opposite direction. So can I say, for a fixed mirror, whatever velocity you will have along the normal, the image will have equal and opposite velocity along the normal. If you have a fixed plane mirror and you are going away from the plane mirror with a velocity u, then the image will also go away from the plane mirror with the same speed but in opposite direction. So you will have the same magnitude of velocity but opposite direction. And to understand that, but the relative velocity of image with respect to object will be 2u. Why? Think of it. Let's say you are standing at a distance of 10 meter in front of a mirror. And you start moving towards the mirror with a speed of 2 meter per second. I ask you after how much time you will reach the mirror. You will say, I will reach the mirror in 5 seconds. 10 divided by 2, 5 seconds. If you are standing at a distance of 10 meter in front of the mirror, your image will be formed at a distance of 10 meter behind the mirror. At time equals to 5 seconds, you would have reached the mirror. You will be standing next to the mirror. And your image will also be standing next to the mirror. I ask you, in the same time frame of 5 seconds, the distance between you and mirror decreased by 10 meter, but the distance between you and your image decreased by 20 meter. So if in the same time frame of 5 seconds, if the separation between you and your image decreases by 20 meter, what is the speed of your image with respect to you? You will say, I am fixed, I am static, I am not at all moving. As seen by me, I am fixed. This mirror is coming towards me as well as the image is coming towards me, and as seen by me, this image travels a distance of 20 meter, 10 plus 10 in 5 seconds. So the image must be coming towards me with a speed of 20 by 5, that is 4 meter per second. Or you can simply use relative. You will say that if the person has a velocity v towards the mirror, then the image will have the same magnitude of velocity but in opposite direction. If I take this direction as positive x, I will say that velocity of image with respect to object equals to velocity of image minus velocity of object. Velocity of image will be written as minus vi cap minus velocity of object, that will be vi cap. Towards object has got velocity towards positive x, image has got velocity towards negative x. So you will say that the velocity of image with respect to object will be minus 2 vi cap. So that's what we are trying to establish here. When the object moves with a speed u towards or away from the plane mirror, then the image also moves towards or away with the speed u, but relative speed of image with respect to object is 2u, given that the object has got velocity along the normal. What happens in the other case, we'll discuss later. Now let's think of the second case, when the mirror has got a velocity along the normal. So when a mirror moves towards the stationary object with speed u, the image will move with a speed 2u. So if you have got an object at rest, and let's say the mirror moves towards the object with a speed u, then the image will move towards the object with a speed 2u. Survive. Simple argument. Let's say this distance is 10 meter initially. So this distance will also be 10 meter. If the mirror moves at a speed of 2 meter per second, I ask you how much time it will take for the mirror to touch you. You will say, sir, 5 seconds. In these same 5 seconds, once the mirror would have touched you, the image would be just next to you. So when the mirror has traveled a distance of 10 meter, your image would have traveled a distance of 20 meter. If the image travels double the distance in same time, its speed has to be double. So if the mirror has a velocity u along the normal, then the image has a velocity 2u along the normal. Notice that the mirror and the image has the velocity in same direction, and this is important. Once more, making you remember this concept. If the object has a velocity u along the normal, then the image has a velocity minus u along the normal. If a mirror has velocity u along the normal, then the image has velocity 2u along the normal. Once more, pause it, revise it. If the object has velocity u along the normal, then the image has velocity minus u along the normal. Same magnitude, opposite direction. If the mirror has velocity u along the normal, then the image has velocity 2u along the normal. But sir, what if the object has velocity parallel to the plane of the mirror? Or what if the mirror has velocity parallel to its plane? So let's see those cases as well. So now we have discussed that when the object moves and the mirror is at rest, if the object moves with a velocity v, the velocity of image due to the velocity of object along the normal will be opposite for image. So if the object has a velocity v, image will have velocity minus v. Now let's think of the next case. What if the object has a velocity parallel to the plane of the mirror? If you start walking parallel to the plane of a mirror in front of it, and you look at your own image as you walk, what can you say about the speed of the image? So sir, if I move in front of a mirror such that my velocity is parallel to the plane of the mirror, I have observed that my image also moves with the same velocity. So that's the idea. So if the object has any velocity parallel to the plane of the mirror, the image has the same velocity parallel to the plane. If you place your hand in front of a mirror and move it parallel to the plane of the mirror, let's say towards right or up or down or towards left, then the image of your hand also moves with the same velocity parallel to the plane, right? So if the object has a velocity parallel to the plane of the mirror, the image also have the same velocity parallel to the plane of the mirror. Okay, so if the object has velocity along the normal, image have the velocity of same magnitude but in opposite direction along the normal. If the object have a velocity parallel to the plane of the mirror, the image have the same velocity parallel to the plane of the mirror. So if I ask you this question, that there is a person who has a velocity of 5 meter per second along the normal, 2 meter per second parallel to the plane of the mirror, what will the velocity of image will look like? So you will say that, sir, the velocity vector along the normal will flip. So here the image will have velocity of 5 meter per second towards left and a velocity of 2 meter per second in the same direction parallel to the plane. Now let's see the next case when the mirror is moving. Let's say the person is at rest, but the mirror is approaching the person with a velocity v. So we have learned that if the mirror has a velocity v along the normal, then the image will have a velocity 2v along the normal in the same direction as the velocity of mirror along the normal. So if the mirror has a velocity along the normal, the image has double the velocity along the normal and the direction is same. So if the mirror has a velocity towards left v along the normal, then the image will have a velocity 2v along the normal towards left. The next case, what if the mirror has a velocity in its own plane? Think that you are holding a mirror in front of you and you move the mirror parallel to its own plane. What will happen to your image? Your image will move with the mirror or will your image not move? Try it out. Take a mirror in your hand or any steel plate for that matter. Move it in its own plane. When you move the mirror in its own plane, your image doesn't move. When you move the mirror in its own plane, your image doesn't move at all. So if the mirror has a velocity in its own plane, then there is no impact on the image velocity due to this mirror velocity. So no contribution of the velocity of mirror along its plane to the velocity of image. So if the object is stationary and the mirror has got any velocity in its own plane, then that velocity is useless. Because of this velocity, the image doesn't move at all. So let's practice out two questions to understand this thing better. So the first example goes like, there is a person who has got a velocity of 4 meter per second towards the mirror along the normal, 3 meter per second parallel to the plane of the mirror, and the mirror has got two velocity, one velocity of 1 meter per second towards the normal and one velocity of 5 meter per second in its own plane. Now tell me, out of these four velocity, which velocity has got no impact on the velocity of image? Out of these four velocities, which velocity has got no impact on the velocity of image? The velocity of the mirror in its own plane. So this velocity of 5 meter per second is time pass. It has got no usage in finding the velocity of image. Now I know that the velocity of image parallel to the plane of the mirror will be same as the velocity of the object parallel to the plane of the mirror. So this velocity will be 3 meter per second. Now let's talk about what will be the velocity of the image along the normal. Now think of it one by one. First of all, think that just the object is moving. So if the object has got velocity of 4 meter per second towards the mirror, the image will have velocity of 4 meter per second here. And now forget the velocity of the object and think of the velocity of the mirror. So if the object is fixed and the mirror goes towards left with a velocity of 1 meter per second, then because of this velocity of mirror, the image will have a velocity of 2 meter per second towards left. So 4 meter per second due to the motion of the object plus 2 meter per second due to the motion of the mirror. So this image will have a velocity of 3 meter per second parallel to the plane of the mirror and a velocity of 4 plus 2 6 meter per second along the normal. If you visualize the image, it will have a velocity of 3 meter per second parallel to the plane of the mirror. Because this velocity of 5 meter per second is useless, the image will have the same velocity parallel to the plane of the mirror as the object, which is 3 meter per second. Now along the normal, due to the motion of mirror 1 meter per second towards left, you get 2 times that velocity, 2 meter per second towards left. And due to the motion of object in the opposite direction 4 meter per second, so you get 2 plus 4, you get a net velocity of 6 meter per second. And if they ask you net velocity of image, your answer will be under root of 3 square plus 6 square. Let's see one more example. Let's say these are the 4 velocities given. The velocity of object along the normal 4, velocity of object parallel to the plane of mirror 6, velocity of mirror along the normal 1, velocity of mirror parallel to its plane is 11. Now first of all tell me, out of these 4 velocities, which velocity won't contribute to the velocity of image? So sir, this velocity of 11 meter per second is useless. The velocity of mirror in its own plane is useless. Now you can say that the velocity of image parallel to the plane of mirror will be same as the velocity of object, so that will be 6 meter per second sure. Now let's talk about the velocity of the image along the normal. So you will say that, sir, first of all assume that this mirror is not moving. So because of the velocity of object of 4 meter per second towards the mirror, the image will also have velocity of 4 meter per second towards the mirror. So due to this 4 meter per second, you get a 4 meter per second here. And due to the velocity of mirror of 1 meter per second away from the object, the image will move with double the velocity, same direction. It will have a velocity of 2 meter per second here. So think of the resultant of these two, 4 meter per second towards left, 2 meter per second towards right. You get a net of 2 meter per second towards left. So if you haven't got these 2 examples, beta, I say in optics, in thermo, what is important is the theory. So remember the 4 steps which I told you, and if you can't understand any one of them, visualize there. Practicing more question is not at all important here. What is important is understanding the theory really beautifully. Now let's see the next frequently asked out case of what is the time on the image of an unnumbered clock. And this is again a very simple thing. So time in the image of an unnumbered clock. So let's say you have got this standard clock, and this clock right now shows you a time of 3 o'clock. The hour hand points on 3 and the minute hand points at 12. Now if we think of the image of this particular clock in a mirror, then the image will look something like this. We know that this hour hand will be flipped, so this will point now towards left, and the minute hand, which is pointing upward, will still point upward. So if I ask you what is the time on this clock, you will say that the hour hand points at 9 and the minute hand points at 12. So the time on this clock has to be nothing but 9 o'clock. So what the time will appear on the clock? 3 o'clock. And the time on the image will be 9 o'clock. Similarly, let's say you have got this clock, and I ask you what is the time on the clock, you will say that the hour hand is between 6 and 7 and the minute hand is pointing at 6, so the time has to be 6:30. Now if we think of the image of this particular clock, so you need to understand that the minute hand will still point downwards, but this hour hand will flip. So once it flip, it will point somewhere here. So now this hour hand will be somewhere between 5 and 6. And the minute hand points at 6. So the time has to be nothing but 5:30. So sir, is there an easier method to solve every time? There is a very easy method. Just remember that the time on the clock and the time on its image, when added together, becomes 12 hour complete. So the sum of the time on the clock and its image is 12 complete hours. 12 hour 00 minute 00 second. So remember just this thing. Here I gave you example of 3 o'clock plus 9 o'clock. When you add these two times, 3:00:00 plus 9:00:00, you get 12:00:00. If you add 6:30 plus 5:30, what you get is 6 plus 5, 11, 30 plus 30 becomes 60:00, and 60 minutes is nothing but 1 hour. So it should be reported as 12:00:00, right? So let's practice out some questions based on this. This is easy. So if the object clock shows us 2:30, what will the image clock show us? So sir, the final answer has to be 00:00. So as to get 00, here you should add 30 minutes more. So when you add 30 minutes more, you have got 30 plus 30, 60. 30 plus 30, 60. But here the remaining part should be 11, not 12. So you will say that 2 hour 30 minutes plus 9 hour 30 minutes gives me 11 hour 60 minutes, which is as good as 12 hour. So if the object clock shows us 2 hour 30 minutes 00 second, then the image clock will show us 9 hour 30 minutes 00 second. Just make the total sum equals to 12 hour 00 minute 00 second. Let's take one more example. If the object clock shows 6 hour 15 minutes 00 second, then what will be the time on the image clock? So you know that adding something to this 6:15:00, I should get 12:00:00. There are no seconds here, so no second required in the image. There are 15 minutes here, so there has to be 45 minutes on the image. So that 15 plus 45 becomes 60, and that can be completely converted into an hour. But this 15 plus 45 becomes 1 hour. So the sum of this 6 plus something should only be 11, not 12. So 6 plus something is 11. What is that something? 5. So if the object clock shows 6 hour 15 minutes 00 second, then the image clock will show you 5 hour 45 minutes 00 second, so that their sum becomes a 12 hour 00 minutes 00 second. But I am not getting. Let's see one more example. If the object clock shows you 10 hour 20 minutes 12 seconds, now tell me what will the image clock show? Sir, we know that the sum on the object clock and image clock on an unnumbered clock should be equals to 12 hours 00 minutes 00 second. So as to get 00 second, I will have to add more seconds to 12 seconds. Otherwise, I can't convert this whole second into a minute. So as to convert this whole second into a minute, I need to complete 60 seconds. I need to add more of 48 seconds to this 12 seconds so that it becomes 60 seconds, and then it can be converted into a minute. Now tell me how many minutes have to be here. If your answer is 40, that's wrong. Why? Because of this 12 second and 48 second, you will get one excess minute here. So here you need to add just as many minutes so as to make 20 plus something equals to 59 minutes, and 1 minute will come from these seconds. So how many minutes should be on the image clock? So you will say, sir, 39 minutes. 39 plus 20, 59 minutes. 59 plus, due to this 12 and 48, you will get one excess minute, and this becomes 60 minutes. How many are? Sir, this 20 minute 12 seconds plus 39 minute 48 second becomes 1 hour. So we have to complete 12 hours. 10 hours are already there. 1 hour due to this minute and second. So I just need to add one more hour. So the answer will be 1 hour 39 minutes and 48 seconds. Sir, I am not getting. Let's practice one more. If the object clock shows 6 hours 30 minutes 15 seconds, what will the image clock show? So you know that the sum of the time on the object clock and image clock has to be 12 hours 00 minutes 00 second. So the final sum has to be 12 0 0 0 0. So as to make it finally 00 seconds, I should be able to convert the number of seconds into minute completely. So I need more 45 second here. So that 15 plus 45 becomes 60. Now I have got one excess minute due to the sum of these seconds. I have got 30 minutes already here. So as to convert the number of minutes to 00, I need 29 more minutes. So 30 plus 29 becomes 59, and due to this extra minute due to 60 second, I will get 60 minutes, and that can be converted into an hour. Now I have got 6 hours here already. Due to 30 minutes and 15 seconds plus 29 minutes and 45 seconds, I have already got 1 hour extra, and I need the total sum to be 12. 6 are already there, so I need 5 more. So the answer will be, if the object clock shows 6 hours 30 minutes 15 seconds, then the image clock will show 5 hours 29 minutes and 45 seconds. Now let's talk about the minimum height of the mirror required to see the complete image. And I know that all of you remember the answer. So a man of height h, also a woman, of height h requires a mirror of length at least equal to h by 2 to see her own complete image. So the minimum length of the mirror required to see the complete image is half the height of the person. So if the person is 5 feet tall, then the minimum length of the mirror required is 2.5 feet, half the height of the person. But somebody might think, why such a beautiful answer? Why only half the length of mirror is required? The reason is that the distance of the object from the mirror is same as the distance of the image from the plane mirror. That's why only half the length of mirror is required. Let's understand why. Let's say here is the person, here is the mirror, and let's say this is the head of the person, foot of the person, and location of eye of the person. To see the complete image, one ray coming out of the head after hitting on the mirror should enter into the eye of the person, and one ray coming out of the foot of the person after hitting into mirror should enter into the eye of the person. These rays will appear to be coming from the person's image, right? Now the person will look here and say that, okay, I'm looking at the image of my head. The person will look at this ray and say that I'm looking at my feet. Since these two distances are same, d and d, and if the height of the person is h, the height of image will also be h. So now look at two similar triangles, this one, the smaller one, and then the bigger one. These two similar triangles have the same internal angles, but the smaller triangle has a length d while the bigger triangle has a length 2d. Since the height of the bigger triangle is double, its base length will also be double. So if the base length of the bigger triangle is h, then the base length of the smaller triangle has to be h by 2. So visualize the two extreme rays coming, and after reflection entering into the eyes, the two rays will appear to be coming from the image of the observer. Now you can say that if the object stands at a distance z in front of mirror, then the image will be formed at distance z behind the mirror. Now bachcho, visualize the two similar triangles. This is small triangle and this big triangle. You will say that for these two triangles, the internal angles are same. So their sides have to be in specific ratio. Now the height of this bigger triangle is double the height of this smaller triangle. So if the height of the bigger triangle is double, this means that the base length of this bigger triangle is double. And the base length of this bigger triangle is equal to the height of the person. So the height of this mirror has to be half the height of the person. Or there is one more logic. Let's say this distance between the head of the person and the eye is given by 2x, x plus x. And this distance between the foot of the person and the eye is given by 2y, y plus y. Can I say that since these two angles will be equal, these two lengths x and x are equal, and similarly these two lengths y and y are equal. If I think of one line here, normal line, can I say that this length will also be x and this length will also be y? So for a person of total length 2x plus 2y, the height of the mirror required is x plus y. For a person of total height 2x plus 2y, the length of the mirror required is x plus y. This means that the length of the mirror required is half the height of the person. But I personally like the similar triangle analogy better. And let's use the similar triangle analogy to solve a question. So the question goes like, determine the length of the road for which the image of A will be visible in the mirror. So there is a person moving on the road. There is a mirror of length 2 meters. At a distance of 1 meter in front of the mirror, you have placed an object and the name of the object is A. The road on which the person is walking is at a distance of 2 meters along the normal from the mirror. Question is, determine the length of the road for which the image of A will be visible in the mirror. So how to solve? Think of the two extreme rays coming out of A, hitting the mirror and getting reflected from the mirror. So visualize the person, the object, its distance, the mirror length. Now think of two extreme rays coming out of A, hitting the mirror and getting reflected. We know that the angle of incidence will be same as the angle of reflection for each ray. The image of A will appear at the point of intersection of the reflected ray. Now these two reflected rays do not intersect, but their extension will. So let's say this is the point of image. We know that if the object is at a distance of 1 meter in front of the mirror, the image will be formed at a distance of 1 meter behind the mirror. Question is, determine the length of the road for which image of A will be visible in the mirror. So the image of A, which is A dash, will start appearing to the person when the person reaches this leftmost point. And it will keep on appearing till the person reaches this point. So for this whole length, the person will be able to see for any position the image of A, which is A dash in the mirror. So let's call this length as length x dash y dash. Now how to find this length x dash y dash? We will look into two similar triangles. Think of this triangle A dash x and y, and this bigger triangle A dash x dash and y dash. These two are similar triangle. For this smaller triangle, the height of the triangle is 1 meter. For this bigger triangle, the height of the triangle is 1 meter plus 2 meter. 1 meter plus 2 meter. So you will say that the height of the smaller triangle is 1 meter and height of the bigger triangle comes out to be 1 meter plus 2 meter, which is 3 meter. So sir, if the height of the bigger triangle is 3 times, its base length will also be 3 times. The base length of the smaller triangle is 2 meter. So the base length of the bigger triangle has to be 3 times that of smaller triangle. So 3 into 2, 6 meter. Once more, looking into the similar triangle A dash xy and A dash x dash y dash. As the height of the bigger triangle is 3 times, the smaller triangle has got height of 1 meter. Bigger triangle has got height of 1 meter plus 2 meter, that becomes 3 meter. So as the height of bigger triangle is 3 times, the base length of the bigger triangle will also be 3 times. And for smaller triangle, the base length is 2 meter. Hence, the bigger triangle, which has got a base length of x dash y dash, will have a length of 6 meter. So that's all in this first hour of optics. In the next hour, we are going to talk about spherical mirrors, and that's where we are going to talk about Newton's formula that will make you solve questions quickly without even raising pen. See you guys in next hour. Bye bye. So that's all for now. See you guys in the next hour.